All right. What time do you leave the house?
6:45.
So if I text you at 6:30, you're awake and you haven't left the house, maybe. Well, I'll just text you guys at like 4:30 in the morning. It's fine. Just I'll do that. All right, people in the back, come on. No, you guys are fine. Darcy doesn't have a single friend.
It's okay, I can focus.
Okay, Bruce has. Okay, you're good. Okay. You can. All right, so here we go. You have two things in your desk. You have a big fat packet that is full of notes and problem sets and labs and so forth. But I will address your attention to the single paper. You guys see the single paper that kind of looks like this? Yes. Yes, you see it. Margaret sees it. Okay, cool. So basically, instead of making you read this for this morning, because it's a lot of like properties of ionic, covalent, metallic, and network covalent, I just wanted to do the activity, so you got a glimpse of what how we compare and contrast metals versus or metallic bonding versus ionic versus covalent. It feels like they had a pretty good understanding of that from honors chem. I'm just filling it out. Okay. So I am not going through all of this in depth right now. So we have our next unit, which is our last unit. Woo! After this unit on solids, liquids, and properties. And this is like heavily emphasized in there. We do a little bit now, we do a little bit later. I'm asking for you to read this and know most of the properties. But today when we talk about bonding, we're talking structure of bonding and then the properties that happen because of that structure. So I'm going to keep referring to properties. I'm just not going to take my time to write down every single property. You have a full list right now. Cool? And this was the last page, mostly the last page on the MSI because it was regarding like properties of matter or properties of these compounds. So put on top of that, read. Because that first, and if you turn on the back, you see it's like IMFs and organic. That's not important yet. Not important yet. Okay, so that's why I just do the first page. All right, so I'm going to hit the highlights on what you should emphasize from your reading last night. We're going to really try to get the Vesper theory and Lewis dot drawing. Do you remember how to draw structures? Like Lewis dot structure.
Oh, okay.
Yeah. 2, 3, 4. All right, 4 or 5. Okay, so we're going to talk first about why bonding matters. Okay, what's involved in bonding. I have some little like helpful tips up here. It says write. I'm going to tell you specifically what I used to write because some of this other stuff was in your inside. Okay. So specifically, you're looking at ions or just atoms bonding. If ions are bonding, what kind of bond is it? Ionic, right? If atoms are bonding, covalent, right? Ions go with ionic bonds. So we're only talking about the valence electrons really involved with bonding because where are the other electrons? Say, where are the other electrons? In the core, and they can't get out to bond. So we're not going to bond with the core electrons. When we start drawing Lewis dot structures, we're only counting valence. So whenever ions form, specifically ions in this case, we're looking to attain noble gas electron configuration. So if lithium was to bond, what would it do with its electrons? Give away an electron. If oxygen was to bond ionically, what would it do with its electrons? Take what? How many? 2. So it's trying to attain noble gas stability. So in terms of these Lewis dot structures, these are singular. So we write the symbol, and then all we do is draw dots to speak of the valence electrons. So everybody look at hydrogen, sodium, and chlorine, write the symbol, and draw dots for their valences. If you need a QR cable, works. All right, GG, hydrogen. H with a dot, right? Julian, sodium. Na with what?
Two dots.
Why 2 dots? What group is it in? One dot. CJ, chlorine.
Cl with 7 dots.
Okay. Perfect. In college, they might ask you to draw your dots in a specific order, specific way. We generally don't do this lowest level of symbols, but this is us thinking of before we get to the covalent structures. Okay, so really, nothing really new here. Isoelectric again. Iso means what? Same. Isoelectric means, okay, so same electrons, right? Same electron configuration in this case. So we went over this, and this was in your 1 through 90, which some of you guys, I got to give you your scantrons back with that. We generally will have those isoelectric electron configurations over and over and over again because we've now started to form electron configurations of that in noble gases. So again, nothing new here. Now, we talk about octet, talk about electrons wanting to attain octet, aka noble gas electron configuration, except for, so this is octet, except for hydrogen. It's teeny, teeny, tiny, and so it's only got 1 valence electron as it is. There's really no way for it to attain octet, so we give it the duet rule because it will attain, in bonding situations, 2 valence electrons maximum. There are a couple other atoms that are really small, beryllium and boron, and they actually don't always, actually, like almost never attain octet either. So beryllium is good with 4 electrons, and beryllium is good with 4, boron is good with 6. So I don't give them rules like quartet and sextet. It's just remember that they have less than octet. Because when we get to situations where they are in compounds, you'll try to get them octet and you can't, and you get frustrated. Just remember they're okay. Yeah.
Is helium bond?
Helium doesn't bond. Okay.
Okay.
Yeah. It's got 2 valence electrons. It's happy. It's never going to bond with anybody. All right. So far, this is old news. Octet is the rule mostly. Okay, so we're going to just practice with ionic first, review lattice energy, and then we're jumping into covalent. Okay, so ionics are really short and fast because you've got electrons, there's a transfer of electrons, and we draw those electrons on the new symbol. So this is an example of that. You have metals. Why do metals give up electrons? No, but there's a reason why they're more likely to give up electrons. They have what? Lower what? Okay, lower ZEF, lower electron activity. Keep going. Larger atomic radius, so they're like valence shells farther away from the nucleus. Lower ionization energy. Like every single trend we can mention, basically is why it's like sodium is going to give up electrons to chlorine, not the other way around. And we don't really want to say, oh, because it's only got 1 valence electron, or that one's got 7. We don't want to mention that because that's not really the reason. The trends are the reason for this transfer. So what we draw is sodium. Let me get red. Sodium's electron being transferred. So when I draw the arrow, it shows transfer of 1 valence electron to make chlorine have full octet. So to indicate that all those electrons are now chlorines, you put brackets around chlorine, and then since chlorine has gained an electron, it contains a what charge? Okay, 1 negative, and then sodium has lost an electron, so it's a 1 positive. So that's the Lewis dot structure for anything ionic. It looks kind of like this. These are the simple ones. For magnesium and fluorine, we already know what it's going to form. What's the formula for magnesium? Go ahead, CJ, good. What's magnesium chloride? Mg, up here. Mg what? All right, so the thing is, we already know this, so spoiler alert, we know there's 1 magnesium and 2 fluorines that bond to make magnesium chloride. But if you were working through the process of it, you'd have to go, okay, magnesium has how many electrons? 2. And fluorine contains how many? 7. 1, 2, 3, 4, 5, 6, 7. So what you'd realize in the process, like, okay, I can transfer an electron, but whose problem has been solved? Only fluorine, right? So if I transfer that electron, fluorine's happy, but magnesium is still not actually truly willing to do this because it's not itself stabilized. So what has to happen? A second fluorine has to be available for magnesium to also donate, so we can all overall get octet on everybody. So we end up with magnesium with what? 2+ charge. No bracket needed just because there's no shell of electrons to really consider. And then we have 2 chlorines, and there's 2 ways to do this. Either put 2 and then put a bracket with 8 dots around chlorine. And then what's fluorine, singular fluorine's charge? -1. So that's one way to write this out. Or you can do magnesium 2+ bracket fluorine subscript of 2, but indicate that singularly fluorine has a 1 negative charge. Tomato, tomato. With reference to this though, overall, anything that's ionic is electrically what? Balance. Give me a better word for balance, because they're no longer, it's individually the ions are charged, but when it's a compound, electrically neutral is the way we refer to this. And that's because of the cancellation of positive charge and negative charge based on the number of atoms that achieve ions or ionic charge. Thumbs up when I can move on. So that's ionic. I'm going to do a brief review of lattice energy. If you can remind yourself on what lattice energy is right now, talk to your neighbor. 30 seconds, let's go. All right, what 2 factors influence lattice energy? Keep talking. 2 factors that influence lattice energy.
Yes.
All right, Joy, give me the 2 factors.
Size and charge.
Size, and then we'll talk charge product as the charge refers to it. Good. All right, so check. Where are you going to get this information from? The big table I gave you for ionic. Do you see the ionic section? Highlight or star the ionic section. You already know this. We just went through the activity. I will just refer to the structure and function relationship, so structure and property relationship here. Ionic bonds are not true bonds, okay? They are literally just 2 ions sitting next to each other attracted because positives and negatives attract. So they're not really bonds, because bonds are like where things are attached to each other. This is just a structure that has positive and negatives repeating itself over and over again. So we relate the structure to the properties because this is a really strong attraction. Anytime you have positive and negatives near each other, it is like the strongest of all attractions. So if you have a partial negative and a partial positive next to each other, the attraction is strong, but not as strong as a full-on positive and full-on negative. Well, what's even stronger than a 1+ and a 1 negative next to each other? A 2+ and a 2 negative. What's even better? 3+ and 3 negative. The dichotomy of those charges creates an even stronger attraction when your magnitude is increased. So the lattice structure, the lattice energy, is really going to be dependent upon the charges that are present. And so is the melting point. You have a better charged product, your melting point is super high. If you've got a weaker charged product, like 1 versus 9, then you're going to have a lower melting point, but it's still relatively high compared to everything else. So everything is based on the lattice energy or the magnitude of the charged product. All the properties are. So the only property that's kind of weird is, well, we say it's such a strong bond. Well, why can it dissolve in water? Water is polar, right? Remember what polar means? Polar means you have partial negative and partial positive. You have a place in your molecule where you have a disproportionate number of electrons. Polar means partial negative and partial positive. Okay, so we know that these can dissolve in solution. So even if you have a strong lattice structure, you basically have a gang of water molecules attacking you on all sides, and you can't compete with that, because if you have water, I'm not going to draw a million of these, but if that times infinity, okay, infinity, if I have that surrounding me, then what's going to happen is eventually the charged product is not going to be strong enough to hold that lattice structure together, and it will dissociate. So we say they're super strong, but then they dissolve in water, and once they dissolve in water, what can they do? Conduct electricity, yeah. So that's the factor that plays in once the attraction has been overcome. Okay. So lattice energy, please don't write that number down. Really not important. So it's just a number, it's a constant. But lattice energy, again, is based on this energy of attraction. And you'll see this is Coulomb's law once again, Q1 times Q2 over distance. And as a simple reminder, like Joyce said, this energy, this lattice energy, is going to be related to the magnitude of the charge product. I like to call that charge product because it's a little bit more sophisticated, and it's inversely related to the distance between them. What is the bigger difference, though? What's the bigger factor? Charge product, because 1 times 1, or 2 times 2, or 3 times 3, or randomly get a 4 charge, which is very, very rare. Sometimes you'll have like lead 4 chloride. You can have a 4 charge. Those magnitude differences make very, very large mathematical differences within the force, whereas the distances between those charges might differ from 125 picometers to 130 picometers, and it's not really a big difference technically, comparatively, between two ionic structures. So discuss for a second how you think this information, I may have spilled the beans a little, but how you think this information plays into melting and solubility of ionic compounds. Can you think of a situation where something is not soluble? Come up with some examples. Yeah, it's got to be ionic, but it's like an insoluble, like precipitate. Lead what? Lead what? You're just all right, come back to me. Okay, generally, all melting and boiling points for all ionics are generally what? High. That is just you simply saying this attraction is very high. You're going to require a lot of heat to overcome that lattice energy, that attraction. Now, solubility will differ. We have 2 categories, soluble and insoluble, right? Throw it back to Unit 2. Soluble. What types of things are always soluble? Nitrates. What else? Group 1A? Nope. There's only one more. Cat P. Ammonium in this case, but okay. So, did you say that? I didn't see. I didn't hear you. What do you notice about all of these ions? They'll have a 1, either 1 positive or 1 negative, right? So when they bond with something, it's a strong bond, but it's not as strong as some other things that we know to be insoluble. So what are some common examples of insoluble compounds like precipitates? So I heard sulfates. Okay. Probably, yeah, definitely some phosphates. Things with silver, and that's simply because silver's a weirdo, but we'll move on. Lead 2+, lead 4+. Okay, so what you're starting to see is that higher charges are starting to come into play. So if I had lead 4 sulfate, is that what you just said? Let's go lead 4 sulfate. What's lead 4 sulfate? SO4. 2 here, and oops, sorry, that's not right. What do I need this to? It's kind of messy. Let me just rewrite this real fast. And PbSO4 2. Okay, so what's the charge product here? It's technically lead 4, right? And sulfate 8. That is a super, super large charge product. Magnitude is quite high. That's why it's insoluble. Water can't get on that. Water cannot attack that in any way or form to actually pull apart to a significant amount. But you know, I've lied to you before Unit 2. I was like, oh, precipitate, it's not soluble. But then what can I now establish for this to say it's minorly soluble? Something about equilibrium. What's the KSP? Like there's actually, okay, I'm gonna stop reviewing now, but like 2 to the negative 100, like I don't know, it's a super, super small amount, but it truly does, water does get a little bit of a dissolve. Okay, lattice energy review. Okay, so who saw this? Everybody. All right, so you saw that graph. I'm going to explain that graph now, okay? So when we're talking about bonding, we've mentioned the fact like, oh yeah, they achieve octet. Why does that matter? Why do they actually get close enough to each other to bond? It's simply because they lower the potential energy of the individual atoms. The whole goal in life, or compounds, is to lower their energy so they're stable. So as these these bonds are forming, somehow, ionically or covalently, they're going to lower the potential energy as they come together compared to their potential energy original as they were separate. So I'm going to let you read right down to me two first. Make sure you have all your stuff. So basically, potential energy lowers as bonds form. That is stabilizing for the compound. So when you're in your chill zone, when you're low energy, you're more stable. And when you're in high energy situations and stressed, think of it as like just you. This is you, okay? So didn't mean to do that, sorry. Okay, so basically, we never actually calculate the potential energy. We look at the interactions and go, oh, this is a high potential energy situation. This is a low potential energy situation. So if your nuclei are all up on each other, what's going to start to happen? They're going to repel. Is that stabilizing? No, that's high potential energy situation. If your electrons are too overlapping of each other, what's going to start to happen? Repulsion, and that's not stabilizing. So what we have, this is Goldilocks region. It's not too hot, it's not too cold, it's not too close, it's not too far away. Because when the atoms are too far away, like here, hydrogen has a single valence electron, other hydrogen has a single valence electron. Neither of them are stable, so they're in their high energy ground state, technically, but they're high energy states where they're not stabilized by a bonding process. But when the hydrogens are too close to each other, their electrons are overlapping too much, their protons are overlapping too much, they've got a lot of repulsion, so that even heightens the potential energy even more. So when they're that perfect distance between, I'm just going to kind of do this, okay? They're the perfect distance, this is bond length, where the electron on cloud 1 is attracted to the nucleus on atom 2, and then the electron on cloud 2 is attracted to the nucleus of atom 1. There's that perfect attraction, not quite too much repulsion. You get this low potential energy system, which is very stable. That's a hydrogen diatomic molecule now. But there's a certain amount of length that has to be the distance between these radii or these nuclei, and then there's a certain amount of bond energy. So if I'm looking at this as a single bond, right? We know hydrogen looks like this. Do you think diatomic oxygen? How do you think that will look on this graph? Diatomic oxygen. You should sketch this graph if you've not. Label it. Bond length and energy. And then let's overlay diatomic oxygen on there when you get a chance. Try to do this with the same creative pen. Huh? my legend I have to follow. All right, so diatomic oxygen. Do you guys think the bond length is the same, greater, or smaller than hydrogen single bond? Why? Oxygen, yeah, and this might not be common knowledge, I'm sorry if I'm assuming. Oxygen does have a double bond between it. So its bond length should be shorter, but double bonds versus single bonds, energy-wise, what? Higher energy, right? So higher stability as well. So the bond energy is going to be down farther, not just from this axis, continues. So here we go. I'm going to try. Oxygen's going to be on this side. It's going to dip lower because it's going to be greater stability, greater bond energy. And it's going to be on this side of the bond length. No promises I'm pretty here. Kind of like that. It's a little bit to the left of the single bond hydrogen. So where would diatomic nitrogen be? Why? Nitrogen diatomic is triple bonded. And this is going to be just beautiful. I'm going to go with a different, going here, blue. It's going to be even more to the left and down. And a shorter bond. That looks basically the same, but it's a shorter bond. And your energy goes back up to the right. So if I give you a graph, and I'm like, okay, line 1, 2, or 3. 1, 2, or 3. Who has the shortest bond length? Who is it? 3. Who has the smallest bond energy? 1. Okay. And, just another pretty graph. Moving on. All right, so this is just last recap of lattice energy. This is going to happen not only, like I drew covalent, right? Is not only happening for covalent, it's also happening for ionic. So you can have ions that are far apart, not stable, so there's no electrostatic attraction. Too close together, because the protons would be starting to overlap with the other protons, and then the Goldilocks region, right? So this is going to give you, again, your bond, or your atomic radii, essentially, not atomic, ionic radii, that would determine the distance at which they sit. And we've already done all this 2 days ago. Just read and then give me a thumbs up, because I'm not going to spend much more time here. The only thing that I wanted to really re-emphasize was the fact that radius differences are super, super, super tiny. So it doesn't impact lattice energy as much as the charge product does. And you guys saw that on one of your FRQs 2 days ago, Monday, and you guys checked your FRQs. That's it for lattice energy. Magnitude, no charges, radii doesn't matter as much. Oh, I have one more thing for lattice energy. I thought I was done with lattice energy, sorry. What do you really need to know here? Lattice energy is pretty dang negative. Super, super exothermic. Why would lattice energy be exothermic when two gaseous ions come together? Because it's forming a stable compound, something like that. Okay, so lattice energy is super, super exo, because as the two gaseous ions come together, they were high energy, but they form a bond, and now they're low energy. So what happened to the energy? It was released, right? Remember we did that series of steps where you were like, oh, the IE energy, it's the energy it takes to take the electron from a sodium. And then the bond association energy, and then the electron affinity, which is the energy it takes to give chlorine a single electron. Remember we did like those 5 steps when we actually calculated the lattice energy? Yes or no?
Yes.
Yes, okay, so that's what a series of steps it takes to actually calculate the lattice energy. I have an activity, we will do it maybe later this week, but essentially you cannot measure the lattice energy directly. You have to look at all these factors that play into it. And then the heat of formation was one of those factors. Generally, heat of formation, which we throw back to thermochem, we haven't seen that in a while, but we have our 2 individual, whatever their natural state is, elements coming together to make a compound. And so HF delta HF, heat of formation is usually exothermic, because that again is a stabilizing process. So because of all these factors that come together, overall there's a summation that leaves us with lattice energy being very, 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 very exothermic. That's the main topic, the main concept here. So I was going to show you a graph with this. Here it is. So these were our steps we took to prepare something for bonding. Let me start where we did. We took sodium solid and we went to sodium gas. What was that called? Sublimation, and that was endo because it requires energy to turn gas to or solid to gas. And then we took diatomic chlorine and we split it into monatomic chlorine, which was what? Diatomic chlorine to break it apart to monatomic chlorine. Bond dissociation, right? So this was sublimation, this was bond dissociation energy. That again is endo because it requires energy to do that process. And then we took an electron from gaseous sodium to make a sodium plus, which is ionization energy, again endothermic because it takes energy to do that process. And then we took chlorine and made chlorine ion, which in this case is EA, electron affinity. But that's a more stabilizing process for chlorine because then it's a noble gas electron configuration. It's in a stable arrangement. That's exo, which is why we're going down. And then there's heat of formation down here too. But what I want you to really see is the energy that's associated when sodium and chlorine ion get together. Look at that. All that energy that's released when the two gaseous ions get together, what is that called? Lattice energy. It's formation of crystalline solid from gaseous ions. That's your definition of lattice energy. So essentially, you're showing the whole process of how this is forming, and then we calculate the lattice energy associated. And because lattice energy is really, 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 really high, that can give us some insoluble products sometimes. All right, thumbs up with lattice energy. I think I'm done. Okay, star on your paper, metallic. We will talk about metallic in more depth on our next unit. This is just a baby intro here. The big differences with metallic versus ionic are that, yeah, electrons are involved, but they're not static. What's static mean? Stationary, right? They're not stationary. They're able to flow, hence a sea of delocalized or mobile electrons that are present. But what we know about metallic bonds is because these electrons are mobile, you can see that they're freely floating around in this larger overall electron cloud. If I throw some electricity through here, what's it going to do? It's going to transfer, right? It's going to jump from electron to ion, and it's going to transfer through, so therefore it's an electrical conductor. It's also a thermal conductor, because thermal energy is just straight up kinetic energy, right? Energy of motion. And again, electrons transport that energy quite well. And because you have such a vast level of attraction that can occur on many, many, many levels, your electron can be attracted to multiple cation cores. This electron could be attracted to multiple cation cores. You have a very strong lattice. It doesn't look like a lattice in this picture, but actually, you guys saw that little picture in the purple. It doesn't quite look like this, but it has a similar arrangement. It's just the electrons are really tiny. So they have a very strong attraction overall, leading us to high attraction, which means what for melting point? High melting point, high boiling point. Yep. Star metallic. You guys know a lot about metallic already. But it's just I wanted to make sure I can relate the structure to those properties that are so unique about it. Oh, last one I'll relate though. Malleable and ductile, what do those mean? So malleable means pound into a thin sheet. Okay, malleable, think mallet. Malleable, you can hit it with a hammer and it will flatten into a thin sheet. Ductile, into a wire, right? So sheet and wire. And the reason this is even possible is because as you're taking a metal and its electrons are all floating around, and you start to flatten into a thin sheet, like I said, those electrons are mobile, not static, so they can move as you flatten this out and still yield a pretty stable arrangement where they're still attracted to their cation cores. And so as you flatten it, it doesn't disrupt the stability of those bonds. So that's why you are actually able to manipulate this solid. All right, stretch break. Go see somebody. Oxygen break. Oxygen break. Did CJ get one?
Yeah.
Okay. Bring me those extra papers for the slackers front here, please. Put all the extra papers on this desk over here. Stack them up nicely for me so I can get those to his coats. Darcy, sorry, we're Darcy. Darcy, I think I skipped you again. Can you bring me your enema song? Now I'm trying to remember who I saw. Oh, yeah. All right, go back to your seat for me. Back to your seat. All right, we're hitting covalent part now, okay? Covalent. So basically so basically at this point, ionic, you should have a decent background of, read on your properties. Metallic, we're going to really heavily hit that on our next unit, but you should know some of the properties. Covalent is going to be out of life for about 4 days. So not only are we going to understand the structural drawings and the properties, but also all the nuances that come with knowing structure. So once you know structure, you know bond polarity, molecular polarity, tetrahedral, trigonal, pyramidal, intermolecular forces, and properties because of those forces. So once you know a little, you end up accidentally having to know a lot more because of that. Okay. So when these two generally metals or nonmetals come together, no one's gonna give up the electron, right? Why are nonmetals not giving up electrons? They want offset so bad, but give me the properties, the trends. High ZEP, high electron affinity, high electronegativity, high ionization energy. So no one is going to give up the electron. So instead, each one, and we talked about like transfer was the key word for which other bond? Ionic, thank you. There's a sharing here, but it's not one electron that's shared. It's 2 electrons that are shared. So if this is hydrogen, it has 1 electron, and this hydrogen has another 1 electron. When they put them both in the middle, they act like they both have how many electrons? 2, which is duet for this guy. So this internuclear region is where that covalent bond is forming. So this electron from hydrogen 1 is attracted to the nuclear core of hydrogen 2, and this electron from hydrogen 2 is attracted to the nuclear core of hydrogen 1. So that's, in the end, it's stable, which is an energy stabilizing process. Alrighty. That's a what kind of bond if there's 2 electrons there? 2 electrons being shared is a what kind of bond? Single covalent bond, yes. If I put 4 in the mix, that would be double bond. If I put 6 in the mix, triple bond. Okay. And how do we draw these? Please do not draw all these dots. So, like, basically, the example I just showed you was hydrogen 1, hydrogen 2, putting 2 electrons between them. That's just tedious. We usually never draw the dots to represent the covalent bond. We usually draw the single line to represent the single covalent bond. Can we all agree this is how we're drawing this? Yes. If you draw dots, you just be on the short list. Okay, you be on the bad list. The AP exams will accept it. It's just tedious. So, like for example, chlorine, you have 2 with 7 valence electrons. They both are going to end up sharing by putting those electrons in between the nuclei, which occur here. But in the end, we're going to draw it like this. So with this, we have 2 different names for the types of electrons we're dealing with now. So you should know the bond in the middle, those are called bonded electrons. And we're good. And then if you have electrons on the outside, like those right there, those are called lone pairs because they're alone by themselves. Or you can call them non-bonding pairs because they're not bonding. Are we okay on the terminology?
Yes.
All right, let me scroll back up and make sure I don't skip something important. These are called Lewis dot structures. That's another important term. And I know this word probably doesn't mean anything to you yet. Valid Lewis dot structures means something a little bit more in depth than just, oh, it looks right. We'll talk about formal charge, which you read about. Formal charge. We'll talk about that shortly. So in the end, things are going to have octet around them as a combination. The octet will be a combination of bonding and non-bonding electrons that create the octet situation, unless you're hydrogen, beryllium, or boron. Question?
So non-bonding electrons have to dot all of them out, but you're only allowed to line the bonding.
Yeah, so usually we'll line the bonded and we'll dot the non-bonding. In college, like when you have to draw these humongous structures, you can do like chlorine, which means 2, 4, 6, 8. College, yeah. Yeah, that is the most accepted structure. Okay. All right, so again, we already went through this. 2 electrons being shared is single, 4 electrons being shared is double, 6 electrons being shared is triple. What we maybe didn't explicitly state is how that affects bond length and strength. You guys already had a really good idea of it with our little dick drawings, those graphs. But what you should know is that like a single bond is long and weaker compared to a double bond. Triple bonds are the strongest and the shortest. So those are easy, fun facts on multiple choice to get right. And give me a thumbs up and we're good. Long and weak, short and strong. Never mind. Okay. All right, so before we draw, this is a reminder of how bond polarity works. This is one of the most challenging concepts in honors chemistry. Does anybody remember the struggle for bond polarity versus molecular polarity? We're getting ready to do some honors chem, so once you guys are masters, don't help further out because we're going to do this. So I'm going to let you read this first, and then I'll elaborate, okay? So with a covalent bond, the whole rule of covalent is that they're covalent. So break that word down. What's co mean? Together or working together, sharing, okay? Valent refers to valence electrons, right? So we're sharing the valence electrons of the species involved in the compound. Now, sharing can happen equally or unequally. Those are the 2 words you should refer to when you're referencing polar and nonpolar. If you have if you have atoms that are the exact same, like anything diatomic, their electronegativity values are way up here, and they're usually, they will be the same if they are the same atom, meaning they're diatomic. So if we have diatomic species, what are the diatomics? The big 7 in hydrogen, keep going. H2, O2, F2, Br2, sorry, N2, what else did you say? I2 and Cl2. There are 7 of them. Those are all the same atom, so their electronegativity differences are 0 because there's no difference in their electronegativity. So they're going to have a perfectly shared bond. Chlorine versus chlorine, the electrons in this bond, how many electrons does this bond represent? 2. So if I have an electron here, an electron here, they're equally spaced, so each nuclei has an attraction for it. So anything that's diatomic will have an electronegativity difference of 0, and it will yield a nonpolar bond. So there are going to be some things that are bonded that are still nonpolar, but they are not the diatomic species here. So like you could have carbon and hydrogen. Hydrogen's kind of weird with electronegativity because it doesn't always have a strong electronegativity. We know that because we form protons, right, H pluses. So they can still have a relatively, that's supposed to be relatively equal sharing here, where there's a small electronegativity difference, but so small it's insignificant, so it doesn't create a big positive and negative region. It doesn't create a partial positive and partial negative region. So you're still going to have generally equal sharing of electrons because the electronegativity values are similar. So what word can you associate with nonpolar? Equal sharing. Okay, or equal. All right. And would you have a partial negative and partial positive system here? No. Okay. So with polar, opposite of nonpolar, you have some problem in sharing. They're still sharing, it's not equally. So if you had 20 cookies, Chase took 18, I got 2. We're still sharing the cookies. It's just he's a much more greedy for his cookies, right? Well, why? What property is this? Electronegativity yet again, right? So if you have a great difference in the electronegativities of those two bonding atoms, you're still sharing, you're just not equally. So this is an example of that. If I had carbon and fluorine, fluorine is the most electronegative of them all. You can do these predictions with no numbers. So fluorine's going to pull those electrons towards itself just in this bond here, not carbon's like core electrons whatsoever, just the bond situation. And so with that, we don't indicate the electrons moving one way or the other. What we do is we say it creates a dipole moment, and we draw an arrow. You have to draw this arrow like this. The arrow points towards the more electronegative one. And so with that pointing towards the more electronegative one, what you're indicating to me is a partial negative. It's like I'm a lazy 8, didn't quite finish the 8 kind of deal. Lowercase, I think it's lowercase sigma, uppercase sigma. It's a Greek symbol that looks like this. No, it's not that one. I'm not going to try. I'm just going to say this is sigma. This is sigma, partial negative. Okay. So on the other side, do you see this like, oh, positive region? It's like a positive, like a plus sign. Guess which side that is? Partial positive. Okay. And dipole moment has been completed. All you're showing is that there's a shift of electrons towards the fluorine, creating a polar bond. And then if we get to the extreme, like extreme of electronegativity differences, like hugely different in their electronegativity values, they're not actually going to share anymore. Somebody's going to give up an electron, somebody's going to take the electron, and what have we made? An ionic bond. So you see this continuum of I share equally, my cloud is evenly distributed, my electron cloud that is. I'm sharing not so equally, but my electron cloud is kind of just skewed to one side. So this is the electron cloud here. And then I'm so not going to share. Electron cloud gets bigger on anion, electron cloud gets smaller on cation. So it is a continuum. Okay. And I'm moving. That is bond polarity. We will work with that more. What more do I really need to tell you?
there are numbers associated with electronegativity, as you guys saw in your investigations last week. I'm not going to give you all the numbers. What we're going to understand is that very small differences in electronegativity value will lead to a nonpolar bond. Humongo differences are going to lead to an ionic bond, and moderate differences are going to be a polar bond. No one really agrees on what these numbers should be. In honors chem, I think you probably remember me fighting with this. Like, it's kind of like 0.39 or 0.50. It's no one agrees on it because it is a continuum. So, but what we should glean from this though is that as we approach the larger differences, like an ionic situation, the larger the difference in electronegativity will start to lean towards an even stronger and stronger and stronger bond. Like I said, it's continuum. If it's ionic, what's the dead giveaway for ionic is what kind of atoms are coming together to make that bond. Metals and nonmetals. And this is the question that all of my students will miss on their next test, because it'll be like on the line between polar covalent and ionic, and be like, well, I don't know how to tell, because they're only looking at the chart and not using their brain. Because if it's an ionic bond, it's metal and a nonmetal. If it's a covalent bond, it's a nonmetal and nonmetal, so that's kind of your other dead giveaway. I'm talking honors chem, you guys can tell them that. I tell them what everybody's going to miss when I'm teaching it, and then they still don't listen. So I'm like, everybody misses this question, write it down. All right, are we okay here? All right, so here's that continuum yet again. It's you can see the numbers are a little modified, but nonpolar covalent, polar covalent, more polar covalent, boom, ionic, right? So there's a number line, but the numbers can be skewed based on what's bonding or the environment in which it's bonding in, things like that. But if you're on the high side, you have a lot of, or your extent of ionic character is high. If you're on the low side, your extent of ionic character is low. This makes sense. This makes lots of sense. Okay. All right, so I'm going to stop here. And this is your how-to guide on drawing Lewis dot structures. Some of you guys saw this in the reading. I saw you guys wrote some of this down. But take a minute there, and I'm going to modify it in like a couple words on the board, okay? Give me a thumbs up if you have signed up for the AP exam. Like, you know absolutely for sure that your first child on this. Okay, I'll check in a second. Miss Landon is supposed to be sending it to me at 8 a.m., so I'll check in like 10 minutes, okay? All right, you can put your thumbs down. We're good. All right, so here's the simplistic way to think about this, okay? V count valence electrons. Write this down with me. V count valence electrons. 2 S make a skeleton. Now, there are rules for our skeleton. We don't willy-nilly get to choose what goes in the middle of our skeleton. Your skeleton is going to be, your central atom should be the lowest electronegativity value, because it's like, yeah, you get an electron, you get an electron, you get an electron. Like, it's not too greedy. It's going to be willing to share. Yes, the singleton is usually it, but unless you have two single atoms, like a xenon, this guy, if you have this, you have xenon and you have oxygen that are both singletons, you would choose the largest atom to put in the central location versus like oxygen, for example. Xenon is bigger than oxygen. So that's your rule of thumb for skeleton. I'm going to say just choose central wisely. Three, E, add electrons until octet. If you add electrons into octet, you're mostly going to cover the gamut and giving everybody what they need. The weird thing is, hydrogen does not need octet, right? Hydrogen needs duet. And you might come across, once you have every octet, the fact that you have too many electrons on your structure. And once you have too many electrons on your structure, you have to modify it So what we do is just give every octet, then we think again. So V valence electrons, S skeleton, E add electrons into octet, R review and or revise. Basically, do you need to do a double bond? Do you need to do a triple bond? That's your thought process there. Because if you have too many electrons in your structure, it's not a valid Lewis structure. So you're like, okay, well, who can I get to share? Double bond. Who can I get to share again? Triple bond. You can rearrange until you get to the point where everybody has octet and you have your valid number of dots. And then 5. Hold on, this is an acronym. Like, pair repulsion. Oh, dang, I mixed it. Oh. So this is supposed to spell Vesper. Valence shell electron pair. We're gonna put. Okay, hold on. I'm just gonna put a P. This is where I was like trying to put pairs, but I was like, no, we'll do R next. This P stands for pairs. That's when you're like, oh, do I need to put double or triple bonds? That's that one. And then R is review and revise. So this one's double and triple. And I like to do the acronym because it makes sense because you're working with this Vesper theory already. V valence electrons, S skeleton, E add electrons into octet, P do I need to repair like doubles or triples, R review and revise. Now when I'm reviewing it, I'm really reviewing it by looking at number of valence electrons because I need to make sure I do not have over the amount that I'm supposed to have. So that's your general rule of thumb. Now there's some nuances to if you can expand octet, which you can, we all know that's not a secret anymore. You can have some atoms that can expand octet because they have levels of access to d orbitals that others do not. So looking up on the periodic table, when do d orbitals start? 3d, right? The third energy level. Well, who's in the third energy level? Non-metals that could technically have access to other third energy level orbitals. So 3D is where it starts. We're looking in the third energy level. Who's there? Ready when you are. No? Who? Well, give me an L, give me an actual element that's in the third energy level, but could potentially have access to other third energy level orbitals like 3D. Sulfur, keep going. Sulfur, phosphorus, chlorine. No, it's not going to bond covalently. Who's past chlorine? Argon, technically, it may or may not bond, but if a situation occurs, it can expand octet. So here's your rule of thumb. Anything that is phosphorus, sulfur, chlorine, argon, and down, meaning fourth energy level, fifth, sixth, whatever, they all have access to d orbitals. They can expand octet, meaning they can have 10 electrons around them, or 12, or 14. Yeah.
So just not here.
Correct. Yeah, not period 2. I'm just trying to get you guys to see that on the periodic table that correlates with third energy level, which technically has access to 3d orbitals. We're going to draw a couple, just probably 2 or 3 for today. And then I have to stop, because I will not need the formal charge in resonance. Can I go past this? Okay. All right, so I want you to start with drawing carbon tetrafluoride. I'm going to try to review the shapes with you as we go. It's a whole other ball game though, so let's work together. All right, so if you have carbon tetrafluoride, what's your first thought? You have to do what? Count valence electrons. That is the first step, and I swear to you, it's the most important step because at the end you have nothing to reflect on if you don't know how many were to be there in the first place. So carbon tetrafluoride has how many valence electrons? So that's 4 from carbon plus 4 times 7 from fluorine. 32 valence electrons it is. And how does your skeleton look? Carbon in the middle because it's the singleton and it has a lower electronegativity than fluorine. 4, and we're going to call this ligands. Remember that? Ligand, L-I-G-A-N-D-S, ligand. So we've gone through V, valence electrons, S, skeleton, by choosing our central atom wisely. What's next? Add electron lone pairs until octet. Who already has octet? Carbon, 2, 4, 6, 8, check. And then add some dots. Not just some, but we're adding 6 electrons to each fluorine. We have given all fluorines octet, just willy-nilly. We cross our fingers it works out. And as you reconsider pairs, you're like, I don't think I need a pair yet. Let's see what this looks like. Reflect how many electrons are here.
32.
Yay, 32. So it's 8, 16, 24, 32. So this is a valid Lewis structure. So what we need to talk about now is what shape does this take? It is tetrahedral. It is not a T. It is not an X. It is not 2D. It's 3D. So it actually has like a kickstand, like one of the fluorines goes out, one goes up, one goes to the side, and one goes to the back. So it's got a 3D structure to it. So this is a tetrahedral. Think of like a tetrahedron, same difference here, because it has 4 ligands on the central atom and no lone pairs. In Honors Chem, you got a chart cheat sheet to help you with your geometries. You do not get that. It is a visualization exercise. Let's do ammonia, NH3, ammonia. All right, ammonia, how many electrons? 5 plus 3 times 1. So 5 from nitrogens in group 5, 3 hydrogens each in group 1 carry 1 valence electron. That's 8 total. All right, next. Nitrogen in the middle, and does it matter how I put the 3 ligands? Can I put them all like right here? No, so we're still looking for symmetry, right? I can't put them all on the left side like, no, this looks great. We're still looking for symmetry. Symmetrical distribution. So I'm going left, right, and then top just to mix it up a little bit. Hydrogen, hydrogen, hydrogen. Who's happy? Because it already has 2 duet, right? So hydrogens are good. Who still needs octet? Nitrogen, so I put a lone pair here. And how many electrons should I have on my structure? 8, 2, 4, 6, 8. We're good here? You guys good? What's up? Oh, okay. Got you. Yeah, so it doesn't matter how you draw this, you're still assess the situation from wherever you're looking. There are 3 ligands, and there's 1 lone pair. And I did not emphasize this enough. You are only looking at the central atoms, ligands, and lone pair. The central atom is how everything else arranges itself. The central atom is your main focus here. So looking at nitrogen as a central atom, it has 3 ligands and 1 lone pair. So stand up and look like that. I want you to figure out how this looks. Okay, so here's the problem. I'm flipping the structure because I want you to think really what this is. Your head is a lone pair. Okay, stand up. Your head is a lone pair. It's super, super negative. Okay, the negative lone pair is not going to. The negative lone pair is not going to want to be near the bonded pairs. Your bonded pairs are electrons. Your lone pairs are electrons. Ain't nobody want to be around electrons. Repulsion, repulsion, repulsion. So it actually bends your arms down, and then these arms have to be far away from, let's say your leg is the other ligand, right? They'd all have to be like appropriately separated from each other, which we'd have to do like down dog on this, right? So we'd have to actually do yoga. But it looks like a trigonal pyramid, right? It's 3 legs, trigonal. And it's a pyramid because the lone pair is a big bully, and the lone pair repels, 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 and it makes that pyramidal shape. So you heard me say repel, repel, repel. That should remind you of this theory. Can somebody tell me the Vesper theory, what the title is again? Valence, shell, electron, pair, repulsion, right? That's the theory. We're determining molecular geometry shapes because of this theory. If we understand electrons repel, lone pairs and bonded pairs, they're going to come up with a new geometry as they would do that repulsion, and we name the shape because of that. That is the whole theory. Okay. All right, let's do one more. Oh, okay, so I have like 3 minutes left. Okay, so here's what I want you to try. Look on the second. It says RG2. You see that? Look at all this stuff. Oh my gosh, there's so much more to do with you. Oh, okay. Circle these for me. Do you see this? Do you see where I'm look on the board? Do you see where I'm pointing in your packet? Okay, circle 3, 6, 7, 8, 9, 10, 12. So there are what, seven structures for you to draw. Do not forget ionic versus covalent if you have a situation like that. And 7 structures, and then page 418, 43, 45, 55, 65, 79, and 80. All of the odds are in the back of the textbook for you to check. We'll check those tomorrow. Tomorrow's Thursday. Check them either tomorrow or Friday based on what else I need to do tomorrow. So this is booked Wednesday. Of course, this is already on the website. You good?